Welcome to this next video for the reverse engineering course of simplilearn security. This video is associated with the chapter number 13 of the reverse engineering course. Once again, we are going to analyze in detail an application, and particularly in this case, we are going to see how obfuscation works in our example. In other words, we are going to analyze an obfuscated piece of code and try to deobfuscate it in order to understand which parts of the code was obfuscation and which part of the code is the original code that someone tried to protect. So let's start the analysis of the application. But before that, we're going to configure the debugger not to start the analysis of the main module automatically. I'm doing this because I don't want the debugger, actually the disassembler of the debugger, to analyze some tricky sequences of obfuscation, because sometimes it can be effective, so it will ruin a little bit the effect of the obfuscation we created for this example. So let's load it. Let's run the application. We can see a message box that appears asking if, hey, have you found the secret message yet? And if we could press on OK, then the application runs. So let's repeat this step and let's use the message box as a point from where we can start our analysis. We pause and then we can go and explore the information that we can find on the stack. So we're looking for a call to the message box API, and we can find here this is the return address, so we can follow in this assembler. So this is the return address from this call to the message box API. So we can assume that the instruction just before this is the call. So let's scroll up a little bit, and yes, indeed, that's correct. So let's also remove all the analysis for the module. You see now how it looks like. If we go again, follow this assembler, we can see the instruction, but if we scroll up, everything is messed up. This is because of the obfuscation we have created. If we analyze the module, we can see that some parts of the obfuscation are cleaned up, but some others are not. The disassembler cannot understand what really goes on. So I prefer to remove the analysis just to appreciate more the effect of the obfuscation. So let's again follow the disassembler here. And if we scroll up, we don't see the call anymore. But what we know is that a call instruction starts with byte E8. So let's try to select this instruction here, binary edit, and NOP the first 2 bytes. So now we can see the call to the message box API. Still the code above is messed up, but we started cleaning up. So this is a very good point to start cleaning up the obfuscation. So let's scroll up to locate the beginning of this function, set a breakpoint and restart the application. Okay, so let's start scrolling down by stepping over the instructions. So in this case we see a jump here that jumps directly inside the messed up code. So let's start following this code and see what is going to happen. So let's start stepping over and see what happens. We see that it's going to push 30 on the stack. Here it is. Then it jumps up and it pops that value to EX. So now EX is 30. Then it's going to increase EX by 1 and then subtracts 1. So this is like no obfuscation, so we can just clean this code with NOP. Then we jump up, and as you can see, instead of having 30 here to read the address of the process environment block, as we saw before in previous videos, it's going to do the same, but now it has the value 30 hex in EX, so it reads the address of the process environment block. You can see. Then it jumps down, it pushes EX again on the stack. Then it's going to zero out EDX and test if EDX is 0, which is going always to be. So this is a fake condition jump. So we can change this with GMP. So let's continue. Then it's going to add 2 on the value on ESP, where ESP points to. So it adds 2. Then jumps down again, and then another jump. Then it's going to increase EDX by 1, and it's going to check if actually the value on EDX is 1 by doing an indirect check through the test instruction. So basically, if EDX is 1, this jump here is not going to be executed after the test. EDX with this value here, and indeed, so it always knows anyway that EDX is going to be 1 there, so this jump will never be executed, so we can just NOP it. Then it's going to pop the value from the top of the stack on EBX. It's going to jump up. This also jump is always going to be executed because it's affected by the previous test EDX operation. So let's change this with jump. Then it jumps down again. And it's going to read the value, the byte, from where EBX points to, which EBX actually now points to the being debugged byte. So EBX becomes 1. And it's going to check if EBX is 0, and if it's not, it's going to jump and it's going to bring us here. So this is clearly a debugger detection. It's so obvious that we don't need to let it come here and see what is going to happen. So what I'm going to do is I will just NOP this jump. So even if it detects our debugger, this jump is never going to be taken. So let's continue. It jumps up. Then it calls an instruction here, a function, sorry. And we can see that the next instruction is this one here at address 42E70. But is it? So let's see what's going to happen. We step in, and as you can see, it's going to increase the return address by 1. So the real return address, it's not the 42E70, but it's the 42E71. So it increased by 1. And when it returns, you can see the real instruction. So the real instruction starts from 71 and not 70. So we know that the previous byte before that one is a junk byte, so we can clean it up. And we also know that every time this function is called, the next byte is junk, because this function what does is just to increase the return pointer by 1. So let's just continue the execution. Then we see it calls the same function again. So we know that the next byte is a junk byte, so we can directly nop it. And we can put a breakpoint here, because we know that, or we can just nop the entire call, and also here. So let's proceed. Then it calls another function here. Let's step in to see what happens. And this function increases the return address by 2. So we know that the 2 bytes just after that the call to that function are junk. So we can go here and clean the 2 junk bytes, and also the call to that function there. And we can see also that now this function is going to be called again. You can just press enter to see what's inside. So we know that we can nop the call instruction and also the next 2 bytes that follow, because we know these are junk bytes, and just continue what we were doing before. And then we arrive here. So for now we're going just to try and clean the obfuscation, and once we clean it up we're going to return back and see what the code actually is doing. So let's continue. Try and locate obfuscation patterns. We see that it calls this function again. You can just press enter. It's the function that just increases the return address by 1. So we're going to nop the call and the next byte that follows. So you see the real instructions now are revealed. Then it calls this function again that increases by 2. So we can just nop and then clean the 2 junk bytes to reveal the real instructions. And then as you can see, this jumps 1 byte. So the next byte is junk. So we can also clean this here. And now we can see the real instruction. So this jump is going to get here, so we don't need this anymore, since between the jump and the real instruction there is just a nop. So as you can see now, it reads from the PEP address plus 68, which is where the NT global flag is located, as we saw in the previous videos. So it checks again if a debugger is present. You see 70, which means that the process is being debugged, and checks if indeed there is the value 70 with the inverse value of this. So indeed, if you inverse 70, you see this value here. So practically it wants to end this value, to do a logical end between this value and the value that the result is going to be 0. Otherwise, and it actually checks if it's 70. So if it's 70 there and we do an end operation between this value and this one, the result would be 0, so it will know that the process being debugged, because it would verify that indeed in EX the value is 70. So we're going to NOP this, because we know that this is a debugger check that was verified. And we're going to continue. We see that it calls again this function that increases by 1. So we're going to fill it with NOPs, and also the next byte. Then it jumps down to the 42 F2B. So should arrive here, but you see that there are junk bytes here that confuse the disassembler. We're gonna fix this later. Then it XORs EX with EX, so it zeroes out EX, and then it checks if EX is if 0 or not, and then it would jump if EX is not. But of course this is a NOP obfuscation type. Actually not a NOP obfuscation type, it's a fake logical check. So we can just NOP this, since we know that this jump is never going to be taken. Then it jumps up and calls this instruction again that it's going to increase by 2 the return address. So we NOP this and also the next 2 bytes. Then it jumps down. Then again, as you can see here, it's going to skip the next byte, so we know that the next byte is junk, and it's going to get here. So between this jump and this there is actually just a NOP, so we can also NOP this. Then the next byte again is going to be a junk byte. You see it's going to skip 1 byte, so I right click, I also fix this, so I don't need also this one. And again the same, the next byte is just junk byte, so I don't need this instruction here either. And once more the same, I clean the junk byte, and then I evaluate the fact that I don't need this anymore. So we have already arrived at this point here. We have already cleaned a lot of obfuscation, as you can see. So let's see what happens next. Let's continue. You see it jumps up. Then again we see that it's going to skip 1 byte, so we know that the next byte is junk, so we can also clean this jump here. And again the same. As you can see, I'm always cleaning first what I believe is a junk byte, and then I NOP the jump that would skip it. So you see that in all these instructions here, so all these bytes, just one instruction here is the real one that we want. See here, same type of obfuscation again with junk bytes. And again the same here. Just the first byte. And again, first byte is junk, and again same thing. You see now, you can appreciate that obfuscation can be a very good challenge, and it can take a lot of time in order to deobfuscate heavily obfuscated piece of code. So it requires a lot of manual work also from the analysts. It's not something that you can easily bypass with automation, because the variations can be infinite. Let's continue cleaning up all the necessary parts. That we know that there are junk bytes, so we won't have to deal with them later on. So you can see now that we revealed the real instructions here. So in this chunk of bytes, only these instructions are the ones we really need, the original ones. That these are the real instructions, 1, 2, 3, and 4. So you can see that how many junk bytes were applied here to obfuscate the code. So then we jump up, then it jumps down again. Then, as you can see, it calls the function that increases the return address by 2, so we can fill with nops and also the next 2 bytes. Then you can see here again that what it does is a nop type obfuscation. It zeroes out ESI, so if it decreases, it's going to be -1. So of course this is going to jump always. So we just need to change this conditional jump with just the jump instruction. I'm not noping these 2 commands instructions, even if they seem that they are not really needed, because it might later need that in ESI the value has to be -1. We can't know this, but we know that this jump it's a fake check, so it's going to always be executed, so we can safely modify this into a conditional jump. So then we jump up, then it jumps down. So you can see the trampolines we were talking about also in the written part, how are used to execute the instructions one by one, of course, in the same order, but they are not placed one after the other. So it makes it very difficult to follow. Then it's going to loop up. So we see that we cleaned a big part. We can see here that we always arrive now in this loop here. So we can safely set a breakpoint here. So we're going to stop here once the loop is over, just run. And it's going to call this function again that increases the return address by 1. So we can just nop this and also nop the first byte here. Then the same here again, fill with nops, and nop also the first byte, and the same thing again, and nop also the first byte, and again. So you see now how the real instructions are revealed. Now it calls this function that as you can see, it increases by 2 bytes, so we can increase by 2 bytes the return address. So I'm going to the next 2 bytes, and then it calls the message box API that displays the secret message. But have we found the secret message yet? Probably we have, but at this point now, since we have cleaned a lot of code and we have also bypassed the 2 anti-reversing tricks that check if the process is being debugged, we're going to save these changes here, and save as _clean, so we can then load the next clean file, the next clean executable file, so that we don't have to clean everything from the beginning again. So let's search for all intermodular calls. You can see now this call to message box, which is indeed here. You can see now that we have saved the modifications we did earlier, so we can place a breakpoint here where the tricky part of the code starts, and we can run the application. So once we break here, we're going now to start digging a little bit more at the code and see what really this algorithm is doing. So let's start stepping over and analyze in detail what we see. So it pushes 30, then it's going to pop this value onto EX. So what we basically have, let's start taking some notes in order to really understand what's going on. Let's start taking notes. So it pushes 30 and then pops this value to EX. So we can write this as move EX 30. Let's continue. And then, as we see, it reads the value of the address of the process environment block, which is with this segment register here, the FS register, and the value of EX, which is 30. So we can directly write everything as EX so let's proceed. Then, as you can see, it pushes EX. I'm going to write this. Then it zeroes out EDX. We don't care about this instruction here because we know it was a fake jump, a fake conditional check. So we're going to jump up. And it's going to add 2 in the value that it's on ESP at the moment, which is the address of the process environment block. So let's write this as this for now. You can see here this junk byte skipping, so we can clean this byte here that we didn't clean before, and also this one here. See, this goes here, then it jumps down and increases EDX with 1. EDX, just increase EDX. Then this was a fake check again, so we don't need this, and then pops the value to EBX. Then jumps up again. Then we can see here it's trying to skip the next 2 junk bytes, so we know the first 2 bytes here are junk, and we don't need also this here, so we clean more obfuscation, and then it reads the value at where EBX points, which basically EBX points at the beginning of the process environment block plus 2. So what we can actually do here is to clean up the code a little bit more, even if now it's more clear what it really happens. So what we can do is that, since we understand the logic of the code, is that we can rewrite this part as, we can just copy this, we need this, we need this instruction here, then we know that it's going to increase the address of process environment block by 2, and then it's going to actually move to EBX the byte that's in EX. So it actually reads the value of the big debug byte. So we have already turned all this into 3 instructions. Let's continue. And EDX at this point should be 1, so we can just say move EDX1. Then it jumps and it checks if EBX is 0, so we can do test EBX, and if it is 0, as we said, it's going to continue the execution here. So we don't need this because this is the anti-reversing trick, so we're going to skip this. And let's take some notes that at this point also you can see that at this point in EX there should be the value of the process environment block, but we increase this by 2 here. So what we can do is we remove this, so we keep EX as this, which points to the process environment block, and do it like this. And now we can continue. So EX points now to the beginning of the process environment block as here. It adds EX10. Then adds 40, then it subtracts 20, then pushes that value of EX on the stack, and then adds the result, and then pops it back to EX, so it actually does add EX 39. Then it's going to add EX1, increase EX by 1, and then remove 2, so it's like doing dec EX. So we can see that it's going to add 68 to the beginning of the process environment block. And we know that this result is always going to be the same. It's going to always add 68 because these are constants. So we can just change this with add dx68. And then it's going to read the value of the process environment block, of the entity global flag inside the process environment block. So we can write can see. Then it checks if this value is 70 to see if the process is being debugged, but we have skipped this anti-reversing trick, so we don't need to make this check here. Then it zeroes out EX, and this is a fake condition again, as you can remember, so we can just move EX, and then it moves on EX this value here. Let's follow in dump memory address. So it moves to EX this value here. We don't need this because it zeroes out EX and then moves this value, so we're not going to need it. Then jumps up. We can see that it pushes 29 and then pops it to ECX, so it's like doing move ECX 29. Then jumps down and pushes the D word where EX points to. So and then pops the first byte. So what it does, it actually moves to EBX, so we can write move EBX byte I write it like this. As you can see, the first byte here to 3B, so it reads the first byte to EBX. It's the first byte where EX points to, but it tries to obfuscate it here by putting all the D word on the stack and then reading the first byte from there. It jumps up. It's going to move EDI 28 and then add some constants. So EDI becomes 78 and then XORs EBX with the value of EDI. So we can do XOR EBX 78, since the value in EDI will always be 78. Then you can see an op type obfuscation. It pushes EX, then it just XORs EX with EDX, but then it restores the value of EX back, so you can just NOP. This will now have no effect. And then it, as you can see, it restores back the result of the XOR operation between the value, the byte on EBX and the 78, back in the same position from where it read the byte. So it retrieved a byte from where EX points to, it XORs that byte with 78, and then it puts the value and substitutes the original value that it had taken. So if we follow in dump memory address, we see that it's going to now substitute the first byte with a value on EBX. Then, as you can see, it's going to add 4 on EX, then remove 2, subtract 2, which means that it's like it had add 2, and then subtract 1 again. So it actually just does inc EX. You can also clean this code here and write here inc. It's the same thing. Then jumps down again, and then loops up to the push dwp.dscx. This instruction here, which actually we substituted with this one here, this and this. We substitute these two instructions with this one here, this one here. So we can NOP this and change this like this. And then you see this here, it's going to always XOR EBX with 78, so we don't need this. We NOP also everything here, and we write here XOR EBX 78. And then it's going to put the result into EX back to where EX points to. So it's going to substitute also the next byte. It's going to increase EX, and then it's going to loop again. So we can write here loop on this instruction here. So we can write, we can a little bit make our code look better. So it's going to loop here, so this is pretty much clear. There is a loop here. The value on E6 is the counter. It's going to be decreased every time the loop instruction is executed. To loop here is going to be decreased by 1. So it actually reads the 29 hex bytes in total from where AX points to, XORs every byte with 78, substitutes the previous byte with the result, and loops up. So very simple algorithm, obfuscated with too many instructions that make it look something very difficult to understand. So we know that here are the bytes that these are the bytes that's going to XOR. You see? So if we put a breakpoint here where it writes every time the next byte back and start stepping F9, so we stop every time here, we can see here the bytes that are going to be decrypted. So take a look. You see how the bytes are decrypted. And once the loop instruction is not going to be executed anymore, we're going to stop here anyway. So let's remove the breakpoint from here and run. We stop here, we can see now the secret message. Code obfuscation is a pain in the eye. And then it's going to display the message box that asks if we just found the secret message. And yes, we did. And we also managed to deobfuscate the code into something very simple. So it checks for the big debugged byte. It also reads the value of anti-global flag as an anti-reversing tricks. But then it just, if a debugger is not detected, it's just going to perform this loop here, very easy to understand, and decrypt the hidden message. Otherwise, if a debugger is detected, it's going to directly go on the message box, call the message box API, and display this message, but skipping the decryption loop. So the secret message is never revealed if a debugger is being detected. So I hope you really enjoyed yourself dealing with obfuscation and see something in practice. You can understand now why obfuscation is used quite often, also by malware authors, because it's a very good way in order to make our code very difficult to analyze and force the analyst to do a lot of manual work to clean the obfuscation in order to be able to understand what the algorithm is doing. And of course, talking about a general picture of the malware, what the malware should do and what its real purpose. So I suggest you try to do this by yourself again in order to understand how we analyze the junk bytes, how we could understand that the next bytes are junk, so we're about to clean them, so we wouldn't have to deal with the same obfuscation again and again and again. And we also save the changes every time we did. We can also right click and copy to executable all modifications in order to save as _clean2. So now we have a new file, a new executable file with all the final modifications, in which we clean the obfuscation. We also rewrote a few instructions in order to be more direct instead of having more instructions simulating just one. And I really hope that this was a very educative video and you really learned something from it. So that was it. See you in the next video.